In this video, we'll begin our discussion of section 6.1. This will be a review of power series. You covered this at the end of Calc 2, and I know then it's probably you're drowning at that point in Calc 2, trying to just stay afloat. So I'm going to review a few things. I'm going to review a couple ideas up at the front that I just want to show you again now that you've got past Calc 2. Maybe just to look at it again and maybe it won't feel so bad. But this beginning part will be just a review type thing. When we get to assessment type questions and what your homework will look like, your homework will have this beginning stuff, but the assessment will be more focused on diffie-qs. I'll show you that as we go along. All right, so power series, recall from calculus 2 that it's an infinite series of sums. So they usually have this form where it's centered at A, right? And then they do this infinite sum by increasing n to infinity. Now, this series may add up to an actual number, which we call converging. It may not add up to a number, which we call diverging. Here's an example of a power series. We just fill in 0, fill in 1, and we add it up. Okay, so I want to get to the important facts here. This is the stuff from Calc 2. Like I just said, it's convergent if the partial sums converges. So there's a way to tell. And I have some tests that we're going to use. We're just going to use two tests from Calc 2. So if it converges, that means the sum actually adds to something. Or like this limit, here's our sum of adding them together. Okay, interval convergence, there is going to be some interval around A such that when I pick an X around that interval, in that interval, it'll converge. Radius of convergence is the what you would think you have A, and then you'll have an A minus R, A plus R, and everything within that will converge, everything out of it will not converge. Absolute convergence, if the interior of its interval of convergence of a power series converges absolutely. So in the interior of its interval of convergence, a power series converges absolutely. What does that mean? Okay, so if I say we have the internal interval of convergence of power series, in other words, x is the interval of convergence and is not an endpoint of the interval. So what that means, if we have an interval that converges from -3 to 3, that everything inside that interval converges absolutely. If it converges absolutely, what we mean is that I could put absolute value around each term and add them up. So that means absolute convergence. We're not going to touch it here, but just a reminder. And then we have ratio tests and alternating series tests. This is what we're going to actually use to tell if the next three problems converge or not. Ratio test says to create this limit, get an answer. If the answer is less than 1, it converges, absolutely. If it's greater than 1, the series diverges. And if L is 1, the test is inconclusive, tells us nothing. Okay, so, and then we can't use this test because it says the ratio test is always inconclusive at the endpoint A plus R. So when we test our endpoints, which you'll see what that means in a moment, we know that we're not going to use the ratio test to come up with that. Okay, alternating series test, this would be like if I have something like this would be an example that it alternates between positive and negative. We could create here, if that was my sequence, what they're talking about, B sub n would be 1 over n here, if this is what we're talking about, and we have this. So to tell if this series converges, that limit of B sub n must go to 0. Okay, in this case it does. And then it is a decreasing sequence, which goes down as n goes for gets bigger, right, and goes to infinity. So in this case, this series here converges because b sub n, this goes to 0, and then also it's a decreasing sequence. Okay, so that means it converges if we were to put a sum here. All right, so let's do an example. We're going to do 3 of these to just kind of jog your memory of Calc 2, which you may not want to, but we're going to. We want to tell if this converges, and then if it does, find the interval and radius. Okay, so I'm going to use the ratio test. The ratio test says to take the infinity as n goes to, take the limit as n goes to infinity of the fraction a sub n plus 1 over a sub n, and we want to do the absolute value of that. Okay, so we're going to plug all this in. Some of these you're going to want to go off to the side. This one I think is doable here. All right, so we're going to have up top, if I plug in n plus 1 into the sequence, I get 2 to the n plus 1, x to the n plus 1, and all of that divided by n plus 1. On the bottom, we just got plugging in n. All right, I have that. All right, if you notice, we can flip some things around. I'll break it up for you actually, because you may not see it. I can take this thing, okay, I'm going to break this up to 2 times x times 2 to the n times 2 to the x over n plus 1 still. So remember, when I have powers, like these are 2 to the first, 2 to the x to the first, I add them to put the bases together, so I just split them up. All right, now you can see that x to the n, 2 to the n are going to cancel. So I got the limit as n goes to infinity, and we're going to be left with on top 2xn over n plus 1. And then I'm going to put the apps, not yet. Okay, so we'll do that. Perfect. Okay, that looks kind of bad, so I'm going to fix it. All right, so n plus 1 there, droopy numbers. All right, so the only thing based on that will change n is going to be in positive numbers because it goes to infinity. So the only thing that we have to worry about for absolute value would be that x. So I'm going to do this. I get 2n over n plus 1 times x. Right, that x just hangs out because it's not being touched with the n. So now from here, we're going to use L'Hopital's rule. Notice that that goes to infinity over infinity, so I can use it. And I get the limit as n approaches infinity of, okay, this is just going to be 2 over 1 times absolute value of x. I can take my limit now. This is 2 times the absolute value of x. Okay, so what we do here, once we get that worked out, we're going to say convergent on, and we're going to take this thing and force it to be less than 1. That's what the ratio test says. If it's all less than 1, wherever it's less than 1, it will be convergent. So this is the absolute value is less than or equal, put equal to for no reason, 1/2, which tells me actually negative 1/2, x is caught between negative 1/2 and 1/2. That's what the absolute value tells us. So we know that that's our interval. But we have to check the endpoints, and this is going to be using other rules, not what we just used. So at x equals negative 1/2, okay, the series, we'll type this in, put this in. So we'll put negative 1/2 in for x. We're going to get n equals 1 to infinity, right? And then we're going to plug that in. We get negative 1 to the n over n. That's what happens if we plug in negative 1/2 into the series up here, right? Well, that converges by the alternating series test. Alternating series test. That's what we talked about earlier. Notice that the b sub n in this case, b sub n, is going to be 1 over n. Right? That the limit of that thing goes to 0, and then also that's a decreasing sequence. Okay, so we have that one. So we do know that the negative 1/2 converges, but if I plug in at x equals 1/2, the series becomes n equals 1 to infinity, but we're just going to get 1 over n this time. Well, that's the harmonic series that diverges. That one's one just to know by heart. So the series converges on the interval negative 1/2 with the closed to an open 1/2. And in this case, r would be 1/2. So our two answers here, negative half to 1/2, and then r is being 1/2. All right, we're going to do two more like this. I'm just trying to jog your memory on what these things are. Assessment won't contain this, so it will be diffie Qs. All right, I might have a quiz, but other than that. Okay, so we have this next problem here. And again, we are going to use the ratio test. So the limit as n goes to infinity, okay, of a sub n plus 1 over a sub n. All right, so we got to plug that in. It's going to get kind of messy here. The limit as n approaches infinity of, right? And then I'm going to do some things over here. I'm going to take k squared plus k, and I'm going to plug in thinking about n plus 1 squared plus n plus 1. All right, that's going to end up being n squared plus 3n plus 2. All right, so I know here on top, I didn't want to rewrite everything that many times. I get 1 over 3, or sorry, n squared plus 3n plus 2. And then that's going to be times 3x minus 1 to the n plus 1. Oops. All right, and then we are going to do the bottom, which is going to be 1 over n squared plus n over 3x minus 1 to the nth power. All right, so what that becomes, we can see that the 3x minus 1 to the nth will cancel, and I'll only have one of them. And then our 1 over divided by 1 over is just going to flip. So I'm going to get the limit as n goes to infinity of n squared plus n over n squared plus 3n plus 2. And then we're just going to have 1 3x, and we need to put this in absolute value, 3x minus 1. All right, so from there, this is kind of how it works out every time. L'Hopital is going to give us, get rid of the polynomials there. Notice that they're both n squared. If I plug in infinity, I get infinity over infinity, which tells me I can use L'Hopital. And I'm going to use it a few times here all at once. This is just going to get me a absolute value of 3x minus 1. It's going to go to 1 if I keep taking L'Hopital. Okay, so from there, sorry, and then these are kind of bothering me, so I need to fix them. All right, so we have that, and the limit of that thing is the absolute value of 3x minus 1. There is no n left. All right, and then we take this thing, and we want it to be less than 1. So that means it's going to be between -1, no inclusion, 3x minus 1, and it's also less than 1. If you work this out, I add 1 to both sides. I get 0 is less than 3x, which is less than 2. And then that tells me x is between 0 and 2/3. Okay, so I know that that is my interval. Now I need to check the endpoints. So at x equals 0, we get the series k equals 1 to infinity. And if I plug in x equals 0, then I'm going to get, on top, I'll get a -1 to the k power, and then k squared plus k didn't change at all. So there's my sequence, and this converges. How I can tell is because if b sub n, we'll put due due to the alternating zeros test, alternating series. My bad. All right, I can see that b sub n. If you want to write some reasoning down here, b sub n is actually equal to 1 over k squared plus k. Well, that converges, right? That goes to 0 eventually, and then also the series, the sequence decreases. So we have that. So x equals 0, it does converge. And then we have x equals 2/3. Right, that's going to get me a series from k equals 1 to infinity. And if I plug that in, things work out real nice, and I get 1 over k squared plus k. And then this thing converges by the comparison test. I know we didn't really talk about that, but we can think about it real quick. It's not a really hard one to understand. Notice that k equals 1 to infinity of just 1 over k squared converges, right? So if 1 over k squared converges, then that would mean if I add k on the bottom, each fraction is just getting smaller. So it would also converge. So radius of convergence, guess I could just write r equals, is r equals 1/3. And then the interval is 0 to 2/3, both closed since both converged. All right, so hopefully that's ringing some bells for you. Hopefully it feels easier this time. Maybe not. Maybe it's been a while since you've taken Calc 2, or when you were there, you just scraped by, not really ever getting it, and that's okay. I just want to remind you what these power series were, what you did with them. These things are extremely helpful in the real world because, and we'll see this in the next series, in the next video, but we can actually use these to represent transcendental functions. What I mean by that is like sine, any of these weird ones that you can't just plug in like a polynomial and solve. You have to actually know what those things are. All right, we got one more here. So here's our new series. Again, we're going to start with our ratio test. So we'll do the limit as n goes to infinity of the absolute value. Let me straighten that out. Okay, and it's going to be a n plus 1 over a sub n. Right? And we're going to plug this in. So the limit as n approaches infinity. Okay, and then we are going to plug all that stuff in. It's going to be kind of messy up here. I'm going to -1 to the nth over 9 to the n plus 1 times x to the 2 times n plus 1 plus 1. It's kind of gross. Right? And then on the bottom is the same thing, but just not so crazy. I forgot a plus 1 here. Everything just to the nth power, or 2n plus 1 here in the x. All right, if I were to work all that out, right, a lot of things are going to cancel. I got practically everything but -1/9 in that first thing. So we're going to get absolute value, and I'm going to result in a -1/9 times. And then if I do everything there, I'm going to get left with x squared. All right, you can think about it if you were to, this is actually a 2n plus 3. So if I subtract 2n, 2n goes away. 3 minus 1 gives me 2. Is reason why I have x squared. Okay, so we get there. This is actually going to be 1/9 because of the absolute value. And then I can drop the absolute value around x squared because of the squared. So we're going to take this thing and we're going to say 1/9. We want this thing to be less than 1. Okay, what that means here is x squared is less than 9, which means x is less than positive or minus 3. All right, so there is our interval. This is going to be -3 up to x up to 3. Okay, we got to check our boundary now. So at x equals 3, we have the sum of k equals 1 to infinity of -1 to the nth, or k really, 9 to the k times 3 to the 2k times 3. Okay, that's plugging in x equals 3. Well, what happens there is, okay, we keep the sum. I'm going to get that -1 to the k over 9 to the k. Nothing changes there. And then I'm going to get times 9 to the k times 3. All I did was do 3 squared. The reason I did that is the 9k's now are going to cancel, leaving me the sum from 1 to infinity of 3 times -1k. And that definitely diverges because I'm just going to get 3 plus -3. It's just going to go from 3 to 0. Right, so that diverges. So nothing at 3. At x equals -3, if I plug that in, I get k equals 1 to infinity -1 to the k over 9 to the k. Nothing changes there. And then I'm going to get -3 to the 2n and -3 to the first power. Okay, that equals the sum of k equals 1 to infinity. And then let's see what's going to cancel. Oh, I put an n there, but that should be a k. So do you see that's going to get me a 9k if I square that? And that gets rid of that. And I'm going to have a -1 to the k times -3. Again, that's just going to go back and forth between -3 and 0. So the radius of convergence, all right, and that's going to be r equals 3. That's what we got for the radius. And then we know the interval isn't going to contain either one. Interval is -3 to 3. All right, so this should be a review. It might feel new just because I know how the end of Calc 2 feels when you're there. Uh, Please just look it over. I know I went kind of through with the plugging in, but I'm just kind of trying to make this video not the longest thing in the world. Especially you're going to do some practice over homework, so please maybe pause and make sure you understand what happens from like here to here, that kind of thing. It's just a little bit of arithmetic and algebra that kind of cancels it out. So please give a look at that. If you need some help on that, please let me know. I can send some videos of some old Calc 2 concepts going through, of somebody going through it. Like I said, this is just used to remind us of what a power series is, but this section and the next section will be mainly how do you solve diffie-q when the answer is one of these. All right, so we have a few more things to review before we get there. We'll do that in the rest of this video.